or something?
Hello.
Okay, good. Okay, good. I can hear you. All right. Thank you very much. I'm going to the PowerPoint directly. Let's start our session. All right, guys. I think you guys are familiar with me. For those who do not know me, this is the first time maybe you can see my camera video. I mean, I'm not a big fan of videos and social media, so that's why you need to excuse me. I didn't go live directly. There were so many problems at the beginning of our semester. The system was really loaded. The experience was extremely limited. That's why I delayed our live until right before the exam, so that I take your recommendation, or if you have a feedback, or if you have a question. Now let's just go ahead and start our session and take this chapter. By the way, our progress in logic circuit is okay. There is no problem with it. We have a slight problem with programming languages and discrete mathematics. We will speak about them in their time. Yet for logic circuit, there is no problem at all. All right. Today we are going to discuss functions of combination logic or combinational logic. You guys are familiar with the combinational logic. We spoke about its details, and we said that we use expressions, and these expressions can be actually represented in different forms. We spoke about the way to even minimize, but minimize what? Maybe sum of product terms, SOP, or the product of some terms. And these things we spoke about. We spoke also about the use of Boolean algebra in representing expressions, and also in transferring or transforming the expressions into logic circuits. And that's exactly what's happening in real life. Okay? So now, today we will just go through these things as quickly as possible, because they are detailed, yes, but I can explain them in an hour or so. So the idea is, like, we will explain about specific devices or logic circuits we have in combinational logic. We have the half and full adders, parallel adders, comparators. We have the decoders, encoders. We have the code converters, multiplexers and demultiplexers, parity generators, checkers. I may end before the multiplexers and demultiplexers because they are really detailed, and usually if we reach to that side and you are a bit loaded and maybe tired, so maybe we will just stop. That's why I changed actually the timing of the session. Let's just go ahead and discuss the half adder. Do you remember when we explained about the Boolean addition? When we add, let's say, two Boolean variables or two Boolean values, or actually the use of Boolean algebra in addition. Okay. The idea is, like, we have only 4 basic rules, and these rules, 0 plus 0, of course, we speak about Boolean data. We don't speak about arithmetic data here. You need to pay attention. These are digital numbers, not decimal numbers. That's a 0, and if you add 0 to 1, that's 1. 1 to 0, that's also 1. But the problem when we add 1 to 1, we have 1 and 0 carried. So how can we deal with it in logic circuits? We have to create a circuit to do this job for us. Now, let's say this one is carried. This one is carried. I put it aside. Now, just ignore this one. Let me take the pen. Ignore this one, and let's just discuss these. 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 1 is 1. 1 plus 1 is 0. Forget about this one now, for the time being. Which circuit is producing this? Do you remember? The similarity. Okay, if you are typing, I can't see because I'm just zooming all the screen. Okay, if you would like to give a feedback, just say by word, speak, I mean. Okay, so here what we are saying is this is an XOR circuit. Why XOR? In the case of the similarity, it brings us 1, or the output is 1. In case of the similarity, the output is 0. Okay, how about the carry? We will deal with it. But we can use just a basic XOR circuit to get us the summation in this case, the sum. Then we need to deal with the carry. That's the basic idea. So we have something we call half adder, and I will explain why half adder, why not full, in a while. This half adder is able to sum up only 2 bits, 1 bit at a time. That means either a 0 here or 1, or a 0 here or 1, and we sum up a bit with a bit. Just 2 bits to be summed up simultaneously. And what's the output? We can have a sum from the have adder, and we have a carry out. So these are the 2 outputs. Any have adder allows you to get 2 outputs. One of them is the sum, and the other one is the carry out. And we'll explain about the carry out in a while. Now, this is the carry out, exactly the one we disregarded earlier while just explaining about these 2. So we can provide a bit here, just 1 bit, a single bit, and here another single bit. All right. So let's move ahead. How can we design this one in terms of, logic? We can create the truth table, and based on the truth table, we can use our own expressions and design. So the truth table, let's just list down 0, 0, 1, 1. What we learned to do, we have 2 variables, a and b, y, 2 bits only. Okay. So 0, 0, 1, 1, 0, 1, 0, 1. That is all the combinations we have. 0 plus 0 is 0, okay, in the summation. And also in the carry, we don't have any. 0 plus 1 is 1, and we don't have any carry. 1 plus 0 is 1, and we don't have any carry. 1 plus 1 is 0 with 1 carried. Okay, so we are supposed to design these 2 outputs. Now, this one is easy, XOR. It's straightforward. Why? In case of dissimilarity, now dissimilarity in the bits, we get 1. In case of the similarity, then we get 0. All right, how about this? Now look at this, 0, 0, 0, 1. What's the gate that produces this? 0, 0, 0 and 0, 0 and 1, 1 and 0, 1 and 1. That's AND. So this is a gate, an AND gate that gets me A and B, takes you to C out. A XOR B takes you to the summation, or sigma. So again, the summation itself, sigma, can be achieved by XORing A and B, or A XOR B. And for the C out, we can just place a plain and A and B directly. Okay, that's the easiest way to represent a circuit for have adder. So have adder, again, we have 2 outputs. These are the 2 outputs, and we have 2 inputs, 1 single bit for each. All right, so now we have for the summation is XORing these 2 bits, and for the C out is ANDing these 2 bits. All right. Now, for the have adder, we have a problem. I said I will just explain about it in a while. The problem with the have adder is that we don't have a C in, the carry in. C out is the carry out, the carry of the output. This one is carried, if you remember. I said this is a carry. Why? Because we have only 1 bit, and we expect 1 bit to be achieved as a summation. We can't have 2. We just deal with 1 at a time. So 2 means we have to line up 2 beside each other. That means maybe summation, beside it carry out. Okay, so this is the idea. This is the idea. All right, so what we are going to do, this is the carry out. We create it separately, like this, and the summation separately. So we have 2 outputs. All right, but how about the carry in? Because we don't just sum up 2 bits and that's it. That's not possible. It won't help you. Why? Because we have so many applications, and we don't just deal with 2 only single bits at a time. We deal with so many bits, and we deal with things that bring us carry in for summation. So that's why we call it have adder. For full adder concept, we have a carry in for the input, or the input carry. Again, this symbolic diagram of it is summation, same like the previous one we explained about. A and B, same, sum, also the carry out. Only one thing is added here, the input carry Cn. So we have a 3rd bit that allows us to sum up a carry coming from somewhere. So this carry is coming from a previous maybe operation or somewhere before we link it to this adder. If not, we can just ground it or place 0. So this is the full adder. This is the basic representation of it. How can we build it? Let's take its truth table. Again, we always take the truth table. Why? The easiest way for representation and for design. For the truth table here, we have three variables. Why? We have A, B, C. And when we have three variables, that means we have 2 to power 3 possibilities. 2 to power 3 is equal to 8. So we have 8 possibilities. We can go with 4 zeros, 4 ones for the first variable, then 2 zeros, 2 ones for the second variable, 2 zeros, 2 ones, then 0, 1, 0, 1 for the third variable. And I say again, as I explained before in my videos, you could start by 1, 1, 1, 1, then 0, 0, 0, 0. It's up to you, but it is just a matter of convention. I got used to use 0, 0, 0, 1, 1, 1, etc. That's the idea. So you could even swap them. Means what? You could just do this one here, place it here, and then this one the way it is, then A next to that. It's up to you. But what you are used to, or what's the easiest to you, or what your brain is conceiving as an easy and convenient way to you, just use it. So there is no compulsory in here. It's not compulsory. It's just suit yourself base. Okay, so we have these possibilities. Now, again, we are adding 3 bits, not just 2. We have A, B, and C in. When they are all zeros, then the summation is 0 and the carry is 0. How? The basic Boolean algebra, we explained about it, the chapters before. Then if we add 0 plus 0 plus 1, that's 1 for the sum, 0 for the carry, 0 plus 1 plus 0, that's again 0 for the carry add, 1 for the summation. Now here, 0 plus 1 is 1 plus 1 is 1 in the carry and 0 in the sum, 0 with 1 carried. Okay, apply again, 1 plus 0, that is 0 for the carry, 1 for the sum. Again, we have 2 ones here. 0 with 1 carried, we have 2 ones here, 0 with 1 carried, we have 3 ones. It would be 1 for the summation. Why? 1 plus 1 is 0 with 1 carried, so we have 0 with 1 carried, keep that 1 carried aside, then 0, this 0, plus 1, that is 1 with 1 carried, 1 with 1 carried. Alright, how can we design it? Now, we need to design these two. All our representation is based on the output. These functions of these 3 variables. So we have 2 functions of these 3 variables. Now, the idea of the summation is really easy. Why? Because the concept of sum, we just explained about it. It's without carry, of course. It's just XORing. So when we XOR, we get the summation with no carry. So what we are going to do, what's added here is the Cin. For the Cin, if we want to add its effect to the summation, then we just XOR it. A XOR B, all XOR C. Even if you ignore these, it's just fine. But why we are putting them here? Because we have XOR for 2 variables at the time. The XOR gate, if you remember, it accepts only 2 variables at a time. Okay, this drawing is a bit bad. Just ignore it. Just XOR gate. All right. So this is the idea. Now, where are we? Again, so the summation is easy. We can conclude it easily by just XORing all of these. If you are not convinced, just check. Now, XORing. XORing means what? Counting the number of zeros in all of them, if it is even or odd. And the number of ones also in all of them, if it is even or odd. Means what? Whenever you have only one in these 3, or an odd number of ones, then you will have 1 here. Now look, odd number of 1, 1, odd number of 1, 1. Okay, here even number of 1, 0. XOR, it's XOR. It's like parity check, if you remember. All right, again, here we have 1, that means 1. Here we have 2, 0. Here we have 2, 0. Here we have 3, then 1. But Cout is a bit complicated, and you can apply the concept of the design of the Cout as an expression. That means we look for these ones and build the circuit based on it. However, we have an easier way. This easy way is what? Now, we said about XORing. We XOR A and B, A XOR B, and then we get the output by XORing Cn along with them. But however, for the carry out, we have a bit more complicated. Now, the idea is like we have A XOR B. Let's make use of it. When we have the A XOR B, we can take a part of it and then AND it with the Cn, and then we can AND A and B separately, and then or all of them together. Meaning what? The first part is A XOR B and Cn, or A and B. You can revise it, okay? You can revise if this one is true or not, going through the truth table. So we said that we have A XOR B and Cn, or A and B. A XOR B and Cn, that's 0 here. Why? Anything and 0 is 0. A XOR B and Cn, while A XOR B is 0, anything and 0 is 0. Again, you go through all of them, or you can just pick up one of them. Pick up one here to see if it is valid or not. Why? Because I will not ask you to design this one. I will ask you to design it in another way. I'll explain to you in the tutorial after a while. Okay? So now, what we are going to design is just a basic circuit. This is not just limited. We don't have only this kind of design. I could just design it in another way, and I will explain after a while in the tutorial, okay, in the next session. But just try to understand that this is an invented representation based on what we have here. So A XOR B, 0 XOR 1 is 1, and C is 1, so the output here is 1. Why? Because if we have these two, we have OR here, A and B, or A XOR B and Cn. So if any of them is 1, that means the output is 1 directly, right? Because this is an OR gate. So this is a concept, and this is the design, the full design. Do I ask this one in the exam? Usually not. I have better questions to ask. So I wouldn't bother you with this one unless I just give you the circuit and I tell you what does it represent. This could be a question, okay? Like if I give you such a design and I tell you what does it represent, you should tell me this is the carry out of a full adder, okay? And this is the sum. So if all of them together like this, you just tell me this is a full adder. That's it. Or if I give you this one, I'm sorry, where are we? Yes, this one. You just tell me that's a full, that's a half adder, okay? Or maybe I will give you the circuit and I ask you the sum and the C out based on the inputs here. I wouldn't tell you A, B, Cn. I would just like put maybe 1, 1, maybe 1. So what would be the output here and the output here? So expect that type of questions. I don't usually make your life difficult by just asking you to design such a thing in a short exam. I have better questions that test your ability of comprehension during the exam, which are easier for you and also easier for me in the evaluation. All right, let's move a bit. So the idea of full adder can be achieved by this kind of combinational circuit. Okay, combinational means we have XOR gate and gate or gate, whatever, all of them in combination. Now, can we create a full adder using half adder? Yes. How? Now for the half adder, we have A XOR B, the first summation, right? Link it to A or to B, it's fine. One of these two, okay? If you link it, if you connect it to A, then you will need to accommodate for the carry in. And for accommodating for the carry in, what you need to do, you need to place it in the second half adder. One half adder is not enough, so we need two half adder. The first one takes A and B as input. The output of the first one, the summation, will be just input of the second half adder for one of them, and the second port of the half adder here will be the input of the carry in. Now the output will be A XOR B XOR Cn. Okay, this is clear. And the carry out, you need to also improvise here. Improvising means what? I have the carry out of the first one, which is A and B, if you remember. Then you need to OR it with the carry out of the second stage, which is exactly A XOR B Cn. And that is the carry out. Usually I don't ask such questions. It's a bit more irrelevant to our own design because we already have the full adder. We can use it for questions. Okay, how can we represent full adders in practical examples? We can just bring a full adder with some inputs and see. We ask you what is the sigma or summation and what's C out. Now this one is exactly Boolean algebra, with just we have the addition based on Boolean algebra. 1 plus 0, that's 1 in the summation, and we have C and 0, so 1 plus 0, that is 1 plus 0, that is 1, so we have 1 for sigma. How about the C out? We don't have any, that is 0. Sorry, the carry out is 0 in this case. All right. I'm sorry. All right. How about the second one? 1 plus 1, that's 0 with 1 carried, plus 0, that is 0 with 1 carried. Okay, that is the output, that's the representation. I may bring you on the exam a table, and I place for you, let's say, a half adder or a full adder, and I ask you to bring those. It's possible. I brought it before in one of the exams. Okay, the same goes here. 1 plus 0, that's 1 plus 1. Why? Because we have carry in. We have to add it. Plus 1, that is 0 with 1 carried. So 0 with 1 carried. Now the idea is, if you want to apply all this formula, you can do that, but I really do not recommend, unless you get such a thing on the exam. If you get such a thing, you have to apply this formula. Why? There may be a modification of how the circuit look like. It's not necessarily that I would bring you a circuit that represents the full adder. I may bring you another circuit, so you need to analyze it. If I bring you full adder, apply directly Boolean algebra, do not waste your time. Okay, so the parallel adder. Now for the full adder, this is limited. Limited means what? We can just sum up one bit at a time. So A and B, one single bit. That's limited. That's not enough. Although we can accommodate for a carry in, but that's not enough. Why? Let's say if I want to add, let's say A1. Sorry, anyone speaking? Is there any?
Sir, your connection was gone.
Now?
It's okay.
Okay, what did we miss? What did?
It gone almost 5 or 10 seconds.
Oh, 5 or 10 seconds, no problem. That means we didn't miss much. Let me double check. Actually, the problem today, I'm not sure. The cable connection is fine, but it keeps coming and going. And I'm connected to both, actually, the Wi-Fi along with, cable connection keeps coming and going. It's better than the Wi-Fi, that's why. Anyway, if the connection goes, please remind me so that we don't miss our class. We just carry on the way we are supposed to do. So let me just get back. So as I said, what we were explaining here is like the full adder is able to add only single bits at a time. That's not enough. So if we are going to add, let's say A1, A0, okay, with B1, B0, okay, we can't do that. Why? Because we have 2 bit at a time. We only accommodate for 1 here. So we have a concept, we call it parallel adder. A parallel adder is able to do that for us, like this. This parallel adder is based on the concept of cascading. Cascading means what? We take these adders and link them to each other in certain process. So the C out will be the Cin of the second one. The summation will be also somewhere for representation of the first one. So we can call this one, let's say A0, A1, sorry, B0, here, B0. And the first carry, C0. Then we will have some 0. Okay. Then we have A1 here. Okay, then we have B1 here, and the carry out will be connected to Cn which will be C1, this one, and so on. This is the cascading process. This is what I refer to by cascading process. That accommodates for 2 bits. If you link these two together, cascade them, you will get an adder that helps you in summing only 2 bit at a time, not just 1, 2 bit at a time. That will be sum 0, sum 1. So what we will be having here, summation for A, or summer, or an adder for A0, B0, A1, B1. All right. More than that, you need to cascade more. So if you want 4 bits, then you need 4 full adder. Okay, 3 bits or 3 bit length, then you need to have 3 full adder. For 4 bit numbers, we have what we call the concept of parallel adder, and that is applied for 4 bits. You know, in digital circuits, or also in programming languages, we refer to 8-bit length by byte, right? And for half of that, we refer to it by nibble. Nibble means 4-bit. So 4-bit length, that means 4 bits that are connected to each other. And it has a lot of applications. So look at this. For this one, we have, let's say here, I want to add A1, A2, or we read it usually A2, A1, B2, B1. So what we are supposed to do, we need to link them. Link them to what? Now initially this is a full adder. Do not be puzzled by its orientation. It's like just adjusted to its own horizontal view. So what we have is Cn connected to 0. We have the summation here, which is the output. The output here, because we have 2 bits at a time, so what will happen is exactly, we will have the first summation, then we will have the carry out connected to the carry in of the second one, then we will have sum 2, and then we will have the last carry as sum 3. Now sum 3, it is organized this way. Why? Because when we add 2 bit of length to 2 bit, most likely we will get 3 bit as an output, and that is the first summation, the second summation, and the C out. Okay, so this is the way, and we will take just a simple example about it. Look at this. This will allow us to sum up. This is A1, A2, A3, B1, or maybe this one B. Okay, B1 or B0 if you like. B1, B2. Usually I start by B1 here. B1, B2, B3, A1, A2, A3. So what are we expecting? We are expecting 4 sums. Why? A number with 4 digits. It may be 3, but it is likely to have the full length of 4. Let's go through them one by one. So we have B1, sorry, B1 here, yes, is 1. A1 is 1. Now, guys, are you familiar with this representation? This is ground. It means 0 in digital circuit. Grounding means in digital circuit 0. So if you don't have any carry in, it means it's grounded, or its value is 0. Okay? So let's just apply 1 plus 1 plus 0. 1 plus 1 is 0 with 1 carried, so 0. Okay? And then 1 carried, keep this 1. 1 will be transferred to the Cn of the second full adder. So again, 0 plus 1 is 1, plus 1 is 0 with 1 carried. Okay? So this one will be also carried again. All right. To the next one, to the next adder. Again, 1 plus 0 is 1 plus 1 is 0 with 1 carried. From where I got those, is there any problem? I can see some of the comments here. Is there any problem? Is there any problem? Connection is broke again. Can you hear? Now it's okay. All right. Okay. Good. Good. I'm sorry again. It's the problem of the connection. I can just terminate. I can keep it to the Wi-Fi. Couldn't catch the last 5 seconds. Don't worry about the last 5 seconds. I'm disconnecting the cable. The problem is the cable connection is actually more stable. So we are going with the Wi-Fi only. Please notify me if there is any problem. I'll repeat the last 5 seconds. Don't worry, I'll repeat the last 30 seconds. So again, we have this 3 full adders for what? For summing what? Let me explain from the beginning. This is the type of questions usually we ask. Determine the sum generated by the 3-bit, now 3-bit parallel adder in the figure below, and show the intermediate carries. The intermediate carries, which ones? This one, also. This is not intermediate, but these are the intermediate. Okay. When the binary numbers are, so we have these binary numbers. How do we represent them? Now look, this is, here we have these 2 numbers. Let's say this is A, represented by A, this is represented by B. So here we have B1, B2, B3, A1, A2, A3. Now it doesn't matter which one is A, which one is B, it doesn't matter. But what matters is arranging them. Let's say this is B, so B1 is 1, you place it here. Okay. B2 is 1, you place it here. B3 is 0, you place it here, okay? Good. This is A. A1 is 1, you place it this side, okay? A2 is 0, you place it here. And A3 is 1, you place it here, okay? Now sum up. Initially you don't have any carry. Why? Because we are just adding these 2 numbers. We do not expect any carry. So you connect it to 0, okay? Ground here means 0. Now you sum up. 1 plus 1 plus 0. 1 plus 1 is 0, plus 0 is 0 with 1 carried. So the summation is 0, and the carry out is 1. This one is the intermediate. It will be passed to the next adder. All right. So here again, 0 plus 1 is 1 plus 1 coming from the carry. That is 0 with 1 carried. Why 1 plus 1 is 0 with 1 carried? All right. So we have 1 carried. It will be transferred as an intermediate, Cn. Next. So here what we have is 1 plus 0. That is 1 plus 1 is 0 with 1 carried. How do we read the number? We read it this way. This is the MSB, okay? From here, the MSB is here. 1, 0, 0, 0. So we read this is the MSB, most significant bit, and this is the least significant bit, LSB. All right, let's move a bit. What's the time? I don't want to extend too much. So I said about the 4-bit parallel adders, we have a representation for this kind of nibble adding or nibble adder. So for that, we have a whole bunch of 4 bits for A, a whole bunch of 4 bits for B. This is directly available. It's available even in our electronic representation. Today I'll give you in multi-sim some examples how to put these circuits together and use them. So you don't have to draw this one. This one is the representation of 4 full adder, 4-bit full adder. Okay, that's exactly the parallel adder, 4-bit parallel adder. Parallel means what? We are cascading those. Cascading means connecting one to each other, next to each other. That means the output of one of them will be connected to the next. What kind of output here? We have C out connected to C in, C out connected to C in, and so on. So this is the parallel adder, 4-bit. It applies the same concept. So if I have to add 4-bit to 4-bit, I can use this parallel adder, and the same concept will apply. You will get 4 summations and 1 carry out. So for the carry out, we start from Cn0, C0. That's the Cn for the first one. That's C0. Then we have C1, C2, C3, C4. This will be the last summation. Why? Because we read it this way, from the MSB to the LSB. Okay? This is like flipped, upside down. Again, do we have any problem in the connection? I hope not. Oh, please not. Couldn't catch the last. Any problem with the connection? No problem? No, good, good, good. All right. Okay, so let's move a bit. Actually, the connection is not from me. I'm using my office at the university. So I have no way to control the connection. I just unplugged the cable because today, actually we are really unlucky. Today I witnessed this kind of problem, discrepancy in the connection just right before we start our session. Right before we started the session, the connection with the cable started making this problem. Well, it's okay if the Wi-Fi is fine. Let's just go ahead and carry on in our session. So how is the representation of this parallel adder is working? It's exactly the same concept of cascading these full adders at a time. We explained about them. So if I ask you to add 4 bits, then you represent it by this one. It's not really hard to visualize and understand. Or if I give you this representation, you need just to add A with B once, one of them, each bit at a time, and you get the summation, each one at a time, and then you see the carry out. You have to pay attention to the carry in, which will be the carry out, which will be the carry in of the next stage. What does it mean? Let me give you an example. Now, this is the explanation of what I say. Look at this. This is the truth table of this kind of 4-bit parallel adder. Means what? What we have here is AN. AN moves from A1 to 3 or 0, 1 to 3. B goes the same, the sigma goes the same, and CI will be C0, C1, C2, C3. This is the truth table. Truth table applies with the same concept of the Boolean algebra. I will not re-explain this one again, but I will give you directly an example. Example of what? Use the 4-bit parallel adder truth table we gave this one, whatever provided here, to find the sum and the output carry for the addition of the following 4-bit numbers if the input carry C0 is 0. So we don't have carry in. We need to add these two 4-bit numbers. So 1100 plus 1100. Now, if you want to go with it one by one using this truth table, you can do that. Or if you want, you can just apply the same concept here. B1 plus A1 plus C0 and see how things go. It's up to you. Like for n is equal to 1, we have A1, B1, and C0. Means the first Cn, which is 0. What's A1? A1 is 0. What's B1? How do I know? A1 is coincided with A1 here, with the value of A1 here. Okay? Same A2, A3, and the same goes to B1, B2, B3, and that's it. Now, the idea is like, okay, we have A1, we have B1, we know them. We have C0. So 0 plus 0 plus 0, that is a 0 in the sum, and a 0 in the carry. Which carry? C1. Why? Because we are looking for the carry out here. All right. Let's apply next. Now, A2 is 0, B2 is also 0, and C1 is 0. 0 plus 0 plus 0, that's also 0 with 0 carried. Okay, let's take A3. A3 is 1, B3 is 1 here. Okay, this one, only this one. Okay, and A3 is this one. Okay, so 1 plus 1 plus 0. Why? Because we said also the next stage is exactly like this one. C2 is equal to 0. Okay, so 1 plus 1 is 0 with 1 carried. So C3 equals 1. Okay, this is 0. Okay, this is 0. C3 would be 1, like this. Right. Here, again, this one I explained it earlier. 1 plus 1 is 0 with 1 carried. Okay, so 0 with 1 carried. Apply again. Now, what's A4? A4 is 1. B4 is 1. Do not forget that you have C3. So 1 plus 1 plus 1. So 1 plus 1 is 0 with 1 carried, plus 0 plus 1 is 1 with 1 carried. 1 with 1 carried. Why do we need C4? This is the last sigma, the last summation. It would be like this: 1, this one, then sigma 4, 1, then sigma 3, 0, then sigma 2, 0, then sigma 1, 0. That's the final answer, the final number. 1, 1, 0, 0, 0. Okay. Another expansion, as I said. Now, if we want to add more than 4-bit, now we have this 4-bit as represented here. We can add 4-bit with 4-bit. But more than that, let's say I want to add 8-bit with 8-bit. What should I do? I can cascade, again, the 4-bit parallel adder. The same what we did to the full adder, we can do the same concept to the parallel adder. We can do that. That's possible. So we can do the same thing. Just flip it upside down, like not upside down or on its side actually. Leave these inputs upward and they represent A1, A2, A3, A4. If you want to extend, you need to add another one that accommodates for 4, A5, 6, 7, 8. Then C0, like always, connected to 0 unless stated otherwise. That means if we tell you that C0 is not 0, it has another value. And the same thing goes, the last carry would be the last summation, and here is MSB to LSB. If you want to go for 16 bits, then you need 4 parallel adders. Why? Each one will accommodate for 4. So 4 times 4 will take you to 16. Usually I don't ask such questions. It's too complicated for nothing. If you can solve one of those, then it's easy for you to solve the rest, but it takes time. That's not our point during the exam. I may bring you such a thing. Such a question means what? I may just give you such a scenario. I give you these 2 parallel adders for bit parallel adders connected, cascaded this way, and I ask you the output. The output is really simple. You just need to apply the Boolean algebra arithmetic, or the type of the Boolean algebra we learned, adding these bits and just accommodating for the intermediate carries and the outputs. Now, if you think about this one, just apply the Boolean algebra and that's it. All I can do is just asking you about the carry, maybe in the truth table. You will just provide it in an easy way. Then it is just A1 plus B1 plus C0. What is it? A1, 1 plus 0, that is 1 plus 0 is 1 with 0 carry. So this one is 1, 0 carry. Take it to the next stage. A2 plus B2, 0 plus 1, that's 1 with 0 carry, that's 1 with 0 carry, and carry on. So that's exactly the idea. You can just carry on doing all these things one at a time, and do not just forget for accommodating the carry in between, because if you have a carry, you have to transfer it from one stage to another. All right. Let's just leave this the adders. I need to check the time. Let's move to comparator, another type. Comparator is actually a device or a logic circuit that assesses, checks if the quantities that we are inspecting are equal, or if they are not equal, which one is greater and which one is less. That's a comparator. Now the basic concept, if we want to check 2 quantities, if they are equal, then what are we supposed to do? We can XOR the bits. If we have just 2 bits to check, we can XOR them. If they are equal, then what we will get? 0 in the output. If they are not equal, we will get 1. Well, if you are looking for 1 in the output, that means active high, not active low. Instead of the XOR, you can use XNOR. If you remember, the output of the XNOR is 1 when the quantities are equal. Do you remember the truth table? If you are XORing XNORing A, XNOR B, then you will get 1 when they are equal. 0 XNOR 0 is 1, 1 XNOR 1 is 1. Then in case of dissimilarity, it will give you zeros. That is the way we use for the equality. For the equality, we can use an XNOR gate that will get us 1 when they are equal, 0 otherwise. Okay? That's a comparator. It compares quantities. But just tells us that this quantity is equal or not. That's it. How about if I want to check if the quantity is greater or less? Well, we will explain about that, but let's say you are not just checking one bit with one bit. Let's say 2 bits. A0, B0, sorry, A0, A0, A1, or A1, A0, B1, B0. How can I do for that? Comparison for that? What I can do is I can compare the lower bits first, or the LSBs first. Okay, whatever will be here, leave it and check the MSBs. Whatever will be here, leave it, then AND both outputs. ANDing the outputs will be exactly high if they are equal. If the quantities are equal, then the output will be high. Why? Now let's think about it. This one will be 1 if A0 and B0 are either zeros or ones. Okay? And the same goes here. This one will be 1 if A1 and B1 are either zeros or ones. So if you AND these two high, only one case, if those quantities are equal, these two are equal to each other and these two are equal to each other, then the output will be based on AND gate high, and that indicates equality. All right. More than that, you need to do more gates. You need to have more gates for more bits. Let's say you have A2, A1, A0, then you need to add one more gate and include it in ANDing, after all, one more XNOR gate. All right. So we have a ready device for comparison. We don't just apply this one, although this is possible, but we have a comparator that applies 3 processes. The first one is greater than, the second one is equal, the third one is less than. Okay? Now, the idea is like this. The first usually, I have to say this, in logic circuits or in anything related to computation or computer, we usually try to avoid time wasting. Time wasting means what? If you are checking if this number, this one is a number, right? If it is greater than this, okay, we start by the MSB. If this one is 1 and this one is 0, then this one is greater for sure. Why? It has 1 in a higher positional weight. Okay? It has 1 in the higher positional weight. But if they are either 0, both of them are zeros, or both of them are ones, then we move to the next bit. So let's say these two are ones. We ignore these two. We move to B2 and A2. We check. If A2 is 1 and B2 is 0, then this number is greater. If B2 is 1 and this one is 0, then this number is greater. If both of them are zeros or ones, then we have to cancel them and move to next. Okay? We do the same process. We do the same process, and that's a shortcut. That is how the computer does it. It doesn't waste time, actually. It asks us to do this job based on the least or the shortest path. This is exactly the shortest path. We don't do it. The computer does it automatically using this kind of IC. All right. So in case of equality, we have 3 output. In case of equality, this one will be high. If A is greater than B, this one will be high. Okay. If B is greater than A, then this one will be high. All right. Let's move a bit. We explained about this one. Let's say if you are just checking, as I said, it will compare A3 with B3. If A3 is 1, then it is directly the number A is greater than number B. If B is 1 and B3 is 1 and A3 is 0, then directly A is less than B. If they are equal, move to the next bit. All right. So this is just a practical example. I explained about the concept. I don't have to waste time in it. You guys can do it. I'll just give you the first two bits. 0, 0. I can check. So ignore this bit. Move to the next. 0 with 1. Which one is greater? Well, 1 is greater than 0. That means directly it is A is greater than B directly. Okay, this is high. You don't check the rest. There is no need. All right. Decoders. Decoders actually are circuits that give you a high output based on a certain input or specific input, or decoding a specific input. Decoding means what? Running a process of, you can say, Boolean algebra or some kind of digital operation on an input that provides a high only in one case. And in that specific input, we are decoding a rhythm, or we are decoding a scenario. This is the idea. So let me remind you of a circuit we spoke about at the beginning of our chapters, like second chapter, I think. Let's say if I want to design a circuit that produces high for this input, it's exactly I'm decoding this input. It's easy. I can use an AND gate with some specific all high inputs. Now, if all inputs are high, I'm sorry. If all inputs are high, then what will happen? If we AND them, then the output will be high. All right, but I have these two zeros. Invert them. Invert them. So the most significant bit is 1. Next to it, we have 0 inverted. You can use the input active low or active high. It doesn't matter. So you can use it here or here. It doesn't really matter. I mean this bubble, the type of the inverter. The next one also 0 inverted. It would be 1. Then the last one is 1. You don't invert anything. Okay. So this is the idea. How about the expression? The expression is represented this way. A3, A2 bar, A1 bar, A0. Okay. Usually I ask such questions, so you may expect such a question on the exam. Determine the logic required to decode the binary number 1011. Now this one is high, this one is high, this one needs inversion, this one is high. So we have a 4 input AND gate. We have the MSB 1 the way it is, the next to it inverted, so it will be A2 bar, A3 the way it is, A2 bar, A1, A0, all ANDed. That is the decoder. Okay, now we don't have just a decoder like that with an AND gate this way. We may have a bigger decoder. Depends on the application. What are you willing to decode? Decoding means what? In this case, for example, if I want to change from binary to decimal, I'm decoding from binary numbers or digits to a decimal number or decimal numbers. Okay? Remember, binary coded decimal, BCD, if you remember, we have 8421. Do you remember? I assume you remember these weights. 8421. 2 to the power 3, 2 to the power 2, 2 to the power 1, 2 to the power 0. These are the possible ways for the binary coded decimal or BCD. So binary bin decimal. We are decoding binary to decimal. What are the outputs here? We will move from 0 to 15. Why? Now we have 4 inputs. 4 inputs, 2 to the power 4 is exactly what? 16 combinations, right? 16. 16. So if you count from 0 to 15, that's 16 combinations. Because we don't say 1, 2, 3 here, we say 0, 1, 2, 3. These are 16 combinations. Now this one is active low. Do you remember we explained about it? Active low and active high. This is active low. That means here, if 0 is active, this output, not the value, the output. If 0 is active, then only this one will be 0. The rest will be all ones. Why? Because active low. What will be produced here, if you invert 0, it will be 1. If you invert one, it will be 0. That's the idea. Now, this is what we refer to by a 4-line to 16-line. 4-line to 16-line decoder. I asked about this once in one of the exams, and the answers were amazing. So 4-line to 16-line decoder, so you should know what 1 of 16, sometimes we call it 1 of 16. Why 1 of 16? Whatever you input here, it will give you only one value, only one number. Why? Because we are expecting decimal output, not just binary. So it will be one of these 16 values. All right, let's move a bit. Guys, do you hear me? Do you hear? Okay, let me check what you are typing. Because I felt like for a moment that everything is quiet. Okay, good. I felt like it was extremely quiet. I said maybe the connection is lost. Good, it's not lost. Now look, the idea of truth table here, we have 4 variables. So if we have these 4 variables, then we have 16 combinations, and based on these 16 combinations, we need to go 8 zeros, 8 ones, 4 zeros, 4 ones, 4 zeros, 4 ones, and so on. So the decoding function will be what? Now we are decoding what? We are decoding decimal outputs from 0 to 15, 16 numbers from 0 to 15. For A3 bar, A2 bar, A1 bar, A0 bar, all of them, if all of them are negated like 0, 0, 0, 0, then we get 0, right? This is a binary number. If you decode it to decimal, 0, all zeros is 0 in decimal also. Do you remember when I told you this is active low? So all of them will be 1s except for 0, it will be 0. So if you invert, all those will be all those zeros. This one is 1. That means the output will be just 0. Is there anything? I keep receiving these messages. Is there anything? No, it's okay. Okay, good. All right. All right. So again, this is the idea. Apply the same to all of them. You move 1, it will be just 0 at 1. Then the rest of them are all 1s, and you keep going on. This is the secondary diagonal of a matrix. It's like just a matrix. Imagine this is a matrix, and this matrix, we have the secondary diagonal, all zeros until we reach 15, 15 all 1s. Do you remember in hexadecimal? 1, 1, 1, 1. That's 15, so it's just coincided with the 15 here. Do you understand this? I hope you do. Let's move a bit. How can we design a decoder with this kind of binary decimal? It's easy, or it depends on actually your application. I may give you a question based on this kind of binary to decimal converter, or binary decimal, or 1 of 16, for example. So as we said, these are the ways: 2 to 0, 2 to 1, 2 to 3. Sorry, 2 to 2, 2 to 3. I don't want to explain them again. I just said about all these details. Do not be puzzled by what I'm writing here in these slides, because I say them by my words. I put them for you so that if you don't have the book, you just need to go through my slides. That will be enough for you. All right, now look at the representation here. For the representation that we have, I have to explain to you these two. Chip select. Chip select means we may have to deactivate or activate this chip. This is called chip in electronic circuits. So the whole design itself is a chip, and you already know it. So I may activate and deactivate the chip based on chip select 1 or 2, or I may change things based on them. Sometimes we have also enable, enable. And that one we will explain about it also. But now let's say we have an example. Let's just address this example. A certain application requires that a 5-bit number to be coded. Use 4-bit decoders. 4-bit decoders, not just one. If you need more, just use. Like the one in the following figure, to implement the logic, note the enable n is enable function of the chip. Okay, the binary number is represented by the format A4, A3, A2, A1, A0. Now look, we have here what accommodates for 4 inputs, but we need for 5. How can I solve this problem? Well, we can use two of this. Okay? We can use two of these two. This is the enable chip select. I can use chip select for enabling this device. All right. I can accommodate for the first 4 bits from the least significant, that means from right to left, in the first one. Okay, then I connect also another chip, same like this, okay, with A4 to the enable. How? Let me show you the design. This is the explanation. I'll just show you the design. Now look, the problem is like this, because we have only 4, but the question is asking us for 5. So if I have 4, then I have to do something like what we call in English improvise. We need to improvise to find the solution to accommodate 5 instead of 4. So look at the design here. These 4, A3, A2, A1, A0, keep them the way they are. They will represent for us from 0 to 15 the way we know. There is no problem. But the idea is like this. I connect A4 to the chip select 1 and 2, which either enable or disable the binary. Now look, this is active low. So if this one is 0, let me take the pen. If this one is 0, the whole chip will be activated. If it is 1, it will be deactivated. Now think about it. If you have a binary number designed this way, A4, A3, A2, A1, A0, it will work if we only run this lower part when this one is 0. This one will work when this one is 0. That means we are dealing with only 4-bit number. So this one will be activated. Why? Enabling the chip, we have low and low here, active low. It will be activated while this one is low, 0. Good. Let's think about this one. We need to accommodate from 16 to 31, another 15 numbers. Okay, good. Take the same inputs to the same inputs of this one, just take a parallel connection from these inputs to the same like what we did here, okay? Now what we need to do is now connect A4 as an inverted version of it. So A4 bar to the enable here. It will be enable when this one is actually what? If you invert it, what will happen? If this one is 1, this one will be 0. If this one is 1, this one will be deactivated. This one will work. So what we did, we divided something like this. Look, A4 has 2 states, either 0 or 1, right? Any binary number has 2 states, 0 or 1. We activated one binary to decimal decoder when it is 0. Okay, and we activated the second one when it is 1. That's what we did. When this one is 0, then we have 4 numbers. Why? The last or the most significant bit is 0, then you can disregard it. You just have A3, A2, A1, A0. And then when it is 1, we disregard the whole thing here. We move to the next 16. These will be all zeros. In this case, those here will be all zeros. Why? Because we don't have any number. 0 just will be activated. Okay? And that's it. When we disable the chip, we will just get zeros as an output. Okay, you have the zeros here. You have other numbers higher in the positional weight, and that's the design. Do I ask these questions? Most likely not. Most likely not. But you should be able to understand them. If you have feedback, say. Do you have a question before I proceed? You can speak in your mic. Let me just check your. I activated the mic actually, guys. Can you speak? Can anyone say anything?
Yeah, we can speak.
Okay. Is there any question? Is there any question?
I don't think so.
Okay, no questions. We will have like around 10-20 minutes more, and then we will end the session. Okay, so let's just go ahead and carry on whatever we can cover up with these 20 minutes. Let's move on. So again, we explained about the input and output based on the design of this binary to decimal. So binary to decimal will decode based on the input. If you have more than one input, it will just add up the weights. Okay, it will just add up the weights. All right, one thing. This one is very important, and I would like really to explain it in a bit, you can say a couple of minutes or so. In our computing system, we have exactly a decoder. A decoder for what? For assigning the input and output. And input and output of what? Devices. Like what we are using now, the camera, the mic, the mouse, the keyboard, the output, for example, the monitor, your speaker, the side now listening to me. All of these can be activated based on a decoder. So we have a controller, and this controller assigned port address to be decoded. So we have a port address for each of the input that we have, for maybe for the output for printer, we have input keyboard. Keyboard is not an output, it's an input. So we have, because we I/O means input or output. We have the monitor, the output. Monitor could be also input and output if it is touch screen. So it will have an address, will be enabled based on its own address decoding. Address means what? Let's say if we are speaking about something like this. From 0 to 15, I assign these addresses from 0 to 15 to these input-output devices. I can decode it based on their addresses. If I want to send something to the printer, let's say its address is 0, I place here what? 0000, and that's it. I will ask the printer, I will permit the printer to be activated. And that is the way we use it in our system. Usually I don't ask such questions. This is just an example for you to understand. Okay, so binary coded decimal to decimal, BCD to decimal. BCD, as I said earlier, 8-4-1 code, if you remember it. And this is 4 line to 10 line. The difference between this one, binary to decimal, binary to decimal, here. Binary to decimal is that we can go more than 9. Earlier I said binary coded decimal. This is not binary coded decimal, I'm sorry. This is just a binary to normal decimal. Why? Binary coded decimal, we accommodate until 9. The bits, the decimal bits that we know, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, then we are just repeating here. We don't have binary coded decimal as 10. It's invalid. Okay? So that's the idea here. We can convert binary coded decimal to decimal. That's 4 to 10 only. The difference is 1 of 10, not 1 of 16, or 4 line to 16 line. Why? Again, BCD, binary coded decimal, 8421 accommodates for only 10 digits from 0 to 9 inclusive. Okay, and this is the idea. How do I do it? Now, do you remember the BCD codes? 0 is represented by 0, 1, again 0, 0, 0, 1, etc. until 9, 1, 0, 0, 1. This is the decoding. Do you remember? AND gate is possible. So, decoding 0, 0, 0, 0, that means A3 bar, A2 bar, A1 bar, A0 bar. Okay, and you move on with all of them until here, A3, A2 bar, A1 bar, A0. Okay? Now, if you have BCD to decimal or slash decimal, you expect the output to be from 0 to 9 only, not more than that. Okay? And this is the idea. Let's take a direct example. A BCD slash decimal or binary coded decimal 1 out of 10, decoder is given in the following figure. Now we have a decoder here. Okay? If the input waveforms, now this is a good example. Why? Because we have A3, A2, A1, A0 are represented by waves. And as I said in my previous videos, you can regard those as digits. You see the timing diagram. These are digits, digits, here, digits, digits, okay? If the input waveforms given as shown below are applied to the inputs of the decoder, show the output waveforms. So we are looking for the output, but they are fine. Why? Because we decode based on digits. All right, let me take these first. A3 is 0. Look, If it is low in its level, it's 0. If it is high in its level, it's 1. Here, this is the timing diagram. This one is the first digit period. So 0, 0, 0, 0. So what are we decoding? 0, 0, 0, 0 means 0. Okay? Remember that this is active low. Okay? Active low. Means the output here will be 0. I'm sorry. Will be 0 to represent the case of 0, not 1. The rest will be 1s. Active low. Again, active low. Alright. Let's take the second bit. So what will happen? 0 will be 0. The output 0 will be 0. 1 will be high, high, high. This one will be low. The rest, all of them will be high. Let's take the second bit. 0, 0, 0, 1. Okay? So here 0, here 0, 0, here 1. Alright. How will it be decoded? This is representing 1. 2 to power 0. 2 to power 0 is 1. This one will be 0. The rest will be 1s. Or this one will be low. All of them will be high other than this one. Go to next. 0, 0, 1, 0. Well, okay. 0, 0, 1, 0. So we have 1 here. And we have 0 here. What will happen? So we have 0, 0, 0, 0. So 2 will be activated. 2 will be activated. The input 2 will be activated here too. Alright? Why? Because the rest are zeros. 2 will be activated. So 2 will be low, active low. The rest will be all high. Take another number with 2 1s. 0, 0, 1, 1. Okay? 0, 0, 1, 1. 0, 0, 1, 1. So we have 1 at 2. We have 1 at 1. Or 1 provided to 2. 1 provided to 1. So what we have, 2 plus 1, that's 3. So 3 will be low, the rest will be high. 2 plus 1, why? It's binary coded decimal. This is the code for 3, 1, 1, 0, 0, 1, 1 is the code of 3. If you don't know, 2 plus 1, just sum them up. Okay? Let's take another, random, this one. Yeah, this one. Or maybe, yeah, okay. We take this one and this one. Here, 0, 1, 1, 1. 0, 1, 1, 1. So here what we have, 1 with 4 or provided to 4, 1 provided to 2, 1 provided to 1. So we have an input to 1, input to 2, input to 4, all 1s. 4 plus 2 plus 1, that is 7. So we have 7 active low, the rest are all high. Take this one, 1, 0, 0, 0. So 1 provided to 8 or input to 8, 0, 0, 0, 0. Only 8 will be active low, the rest are active high. You can check all, as I just explained, based on all these states. Now, initially, one thing I have to say, I said 0, 0, 0, 0. Now for 0, 0, 0, 0, we have all zeros here, all zeros. So this one will just be activated, only the 0 will be activated, as I said, active low, active low. And this is a counter, by the way. If you check 0, 0, 0, 0, that's 0, 0, 0, 0, 1, then 0, 0, 1, 0, that means 0, 1, 2, 3, etc. Okay? Let's move a bit. We may have also BCD to 7 segment decoder. 7 segment is like when you want to display something with this kind of representation. We will have a part for it later on, not now. For example, these, we can represent all the binary, all the decimal numbers based on this kind of representation. Why? By activating these legs. Okay? We have a binary coded decimal for that. Why binary coded decimal? Because our digits are only limited from 0 to 9, the decimal digits. So we can use BCD as an input, 8, 4, 2, 1 again, and the output will be these 7 segments. It depends. Let's say if we are looking for 9, this one will be activated, this one will be activated, this one will be activated, this one, and this one. Okay? These legs, I'll explain to you later on their arrangement. Not now. We will have some other implementation for them. For the time being, you just need to know they will never come to your exam now, maybe in the final, okay? All right, encoders. Encoders actually do the opposite job of decoders. Means what? They encode, they convert maybe decimal to binary, or they convert maybe letters to binary, or maybe they convert hexadecimal to binary, and so on. That is what we call encoding. And for encoding, we need encoders. So encoders will apply something like decimal to BCD encoder, for example. That's possible. I convert from decimal to BCD, BCD binary coded decimal. 0, 1, 2, 3 until 9, they have their own coded values. That is possible. Now if you look, if you want to design a circuit for this, now look at this. Look at A3. Let's just A3, check it. It is 1 with 8 and 9. Okay? How about A2? It is 1 in 4, 5, 6, 7. Okay? 0 otherwise. How about A1? 2, 3, 6, 7. How about A0? 1, 3, 5, 7, 9. We can AND those. You can AND those, and then you will get that circuit. What does it mean? Oh, sorry, OR, not AND, because we say OR. I'm very sorry. So A3 would be 8 or 9 as 1, either one of them. Okay. Then A2 will take 4, 5, 6, 7. These are the inputs. Okay. Then A1 will take 2, 3, 6, 7. 2, 3, 6, 7. Okay. And the last one, this one, 8, 9. And we said for A0, we'll take 1, 3, 5, 7, and 9. Either one. That's why we use OR, not AND. I mistakenly said AND. It's not AND. Otherwise, we will get 0 all the time in AND. Okay, so this is a simple representation of an encoder. Encoder of what? As I said, these are the inputs. Arrange them from 1 to 9. Okay, of your binary coded decimal, here decimal. So we need the BCD as an output. We arrange our decimal values here, and that will be our output. Okay, that will be just the A3, A2, A1 based on all these combinations. This is a bit complicated circuit. Usually we don't design such a thing. It's a bit more complicated than what we are supposed to design. We have for it a whole chip. This one is available in a chip, otherwise we would really be getting confused with those. Even myself, I got confused somewhere here. So we have a whole chip for it, and it's much easier like this. And this is a chip, what we refer to by highest order or highest priority. And I'll explain about this priority issue. Now, when you see high priority / BCD, it allows you to encode which one comes first from the highest value. It doesn't encode all of them. It doesn't, because actually we are looking for encoding one of those. Not all of them. We can't encode 9 and 1 at the same time. Why 10? 10 is not a valid BCD, right? So we are trying to encode either 9 or 8 or 7 or 6 until 1. Either one of those. So any one of these will be encoded based on its priority. If you see high priority, that means the highest will be granted the output first. Now we have the VCC. VCC is the supply voltage. Let me explain about it, because this chip will need a supply to work, to operate. It's an electronic device after all, so it needs a power supply to operate, and this is the ground. Okay, this is the ground. All right, now look at this. I will just give you a simple example. Maybe we stop right here. Why it's around 2? Yes, after this example we will end the session. All right, now look at this. When we have this kind of priority encoder for the BCD, now what we will look for? We will look for the highest. Now this is the number. count them. 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have 9 digits. You start assigning from MSB or LSB, it's up to you. This is MSB, 0, 0, 1. How do I know? 0, which is provided or input to 9, input to 8 is 0, input to 7 is 1. Okay, then I got the output, the decoded output, 7. You don't have to check the rest. The first one comes will be the output. Now this is active low, remember. Active low will get you, instead of 7, the inverted value of BCD representation of 7. Means what? Now in normal circumstances, what we have, 7 will be 0, 1, 1, 1. Okay, that's good. But now it is active low. It will take the inversion of this. The inversion of this will be 1, 0, 0, 0. That will be the output. Okay. Now again, let's say I provided let's say 0, 1 here, then something x, 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 it doesn't matter, the value here doesn't matter. So 8 will be decoded. It will be what? 1, 0, 0, 0. Okay, that's 8, but it's active low, so it will be 0, 1, 1, 1. Okay, I hope it's clear. Code converter, I think we can keep this one for next time. Let me open the session for questions. Now it's almost 2, enough. I think you guys are already tired. Do you have any question? Do you have any feedback? Would you like to ask anything? Any question?
Excuse me, sorry.
Yes.
Any class 2:30?
Yes, we are supposed to take for tutorial. It will not last for long. Someone told me that he has a driver's license, something. You can go, no problem. That's fine. Okay, but the rest of you, if you do not have anything, actually, you guys are having exactly nothing other than just joining our classes. All right. So if you have an important business that you can't delay, it's okay, you can go. But if you don't have any business, just come and join the class, because I'll speak about things related to the exams. Up to you anyway, if you want to join. Okay. Any other question? Someone is telling me, could you mute yourself? My mic is... If I mute myself, you can't hear me.
No, sorry, it was for Ibrahim.
Okay. Yeah, that was a weird comment if it was to me. Well, no problem. Guys, do you have any other question? Even about previous classes? Are you ready for the exam? Would you like to ask any? Live class, I can't join tutorial teacher. But by the way, I put your classes exactly in the time of the schedule. Who is putting his live session during our class? What kind of class do you have at 2:30? You're supposed to have a class with me. What is the class? Yes. The one said I have a class at 2:30. What's your class? It is during our class time. I took also Introduction to Computer Science. Introduction to Computer Science is not at the same time, is it? Okay, you are permitted, but look, guys, this is the good side. Look, I can. All right, this is a problem. Starts. All of you, that means. Should we change it? Should we change the live for the tutorial? Should we change the life of the tutorial? Vote. Raise your hands. More. Raise your hands. As we are second class, okay, most of us do not, I suppose. Okay. Okay. All right. You guys, how many of you? 1, 2. 1, 2. Let me check. Only 2. Your class starts, you said, at what time? Let me check. You said at what time? That's really a problem. You guys actually should not have a conflict in the timetable, but since there is a conflict, I don't want you to lose your right in having such. We can change the time, I guess. This we can change, but it depends on the majority. Anyway. Now, here's the thing I would like to say. Well, tomorrow we have... oh, wait a minute. Your class is starting again. I'm sorry, because I missed that message. At what time? Introduction to Computer Science. Guys, Introduction to Computer Science.
They say 2 between 6.
2 to 6.
Or,
Oh, 2. Okay, guys, goodbye. So you just go to your class. What I'm going to do, this tutorial is really important. It will be recorded, okay? It will be recorded. Whatever in it will be recorded. I will upload it to the YouTube. But next, because this is we have only this chance before the midterm. I'm not sure if I can make on Friday. Maybe I can make another extra session, but I think you guys are occupied on Friday. Starting from the week next to the exam, I'll try to solve this issue. Everyone means what? You guys are speaking discreet. Everyone means what? All right, let me just check. You can see the messages are not coming to me on this screen. They are coming to me like all of them at once. No problem. Look, here's the thing. Here's the thing. Again, I said, let's take our tutorial today. There is a button on the left, supervised chat. Yeah, yes, that's right. Well, this one is actually for the details of the session, not that one. Well, I can see all the chats. I'm able to see them actually. But the idea is like here, you are referring to this one, I know. But you're referring to all these things, I know. But I'm just saying why it is popping up to me one after another like this. I understand, like, you can just say, we can change, yes. I'm sorry. This is the thing I would like to say. For today, let's have our tutorial on time the way it is. Then we need to check how we can solve this issue of Introduction to Computer Science. Contradicting with this tutorial, because we are supposed to have actually a class during the same time. We actually should not have clash. You guys, those who registered the Introduction to Computer Science should not have been able to register it based on the current timetable. Well, anyway, no problem. I'll just try to manage the thing. I'll just try to manage this possibility of change. Maybe we can make it in the morning, maybe. No problem. I will upload these sessions to YouTube so that you can also check them if you have any problem and refer to them back. I'll upload also the tutorial to the YouTube so that you refer to it. For today we are going to have it, but then we will need to solve it later on. Actually, the live, I put it during the time of my class. If you check the timetable, I just put during my class time. I assumed that none of you is having a clash. But since some of you have this clash, we will try to see how we can solve it later on. But today, let's just move on with the plan. I will keep the video for you on YouTube, so those who cannot catch the tutorial will be able to check it on YouTube. Okay, any more questions, any more comments? I can see there is no here. Any comment? Any question? Okay, so will you upload? Yes, I just said I will upload all these videos, okay? I'll upload them. I'm actually recording it from my own system, and I can record it also here. It's recording, so there is no problem. I'll upload it also, okay? No problem. Okay, no more questions. We can take a break, get back around 2:30, okay? Okay? All right, so we are coming back on 2:30. Those who cannot come on 2:30,